So we have some basic formulas for numerical integration. The idea of numerical integration is I'm not going to work with the function per se, I'm going to work with some data. So I have some sampled data at a couple of points. I want to say, well, what's the best I can do, or at least what's a reasonable approximation to what the actual value of the integral would be if I were able to integrate it. So we talked about three big ideas. Now the first big idea was a repeat from Calculus 1, which is let's do Riemann sums. And so the idea is we're going to take our interval, and in all cases we're doing this, but we're taking our interval and we're breaking it up into small parts. And we're going to break it up from A to B, we're going to break it up into n equal parts. And so we're going to start at A, we're going to call that our initial point, x0, and we're going to run to B, and that'll be our xn. And these points, x0 to x1, x1 to x2, and so forth and so on, they're equally spaced. So that's one of the underlying ideas when it comes to numerical integration, is you should say, well, we want to break things into small parts, so let's just break them up into small equal-sized parts. And you do need that when you get into the more interesting rules, namely at the bottom, Simpson's rule, which we'll get to in a moment. So Riemann sums are actually fairly straightforward. You have a width, that's b minus a over n. And then, for every interval, you have to pick a height. And so you say, okay, I come to my first interval, I pick a height. That's my f of y1. And the second interval is a height, f of y2, and so forth and so on, all the way on. So then the question is, okay, which do you pick for your height? So you have a whole interval. Anywhere, so in particular, if I'm thinking of my intervals, so if this is my ith piece, then what happens is I'm going between, and then my function's up here doing something, I'm going between xi minus 1 up to xi. So this is my ith piece, my ith little strip. So what I can do is I can do one of three things. I can pick the left, well that would be in the ith point, you pick the xi minus 1. Or I could do the right, which would say, if my ith piece, I'll pick the xi. Or you could go in the middle. Now, usually we go with the midpoint. You really can say, look, just pick any middle point. It works. But generally speaking, the halfway point is easy for us because it's consistent. Now, I will say, when it comes to actual data, the midpoint rule does not get used very much. And the reason I say that is in order to use the midpoint rule, you have to have the data at that point. And oftentimes when we have data given to us, we have gaps. And we say, look, I don't know what happened between these 2 points. I can't know. It's not available to me, that information. So I can't use it. So usually we use the left or the right. Then we talked about the trapezoid rule. And the trapezoid says, all right, instead of thinking of rectangles, or if you like, here we have constant functions, we're going to think of the following. We're going to think of lines. So I have one little strip, and I have it doing something on the top. And what I do is I just say, well, look, let's approximate the shape by a trapezoid, but really the top is a linear function. So what do we do? Well, we still have the width showing up. That's the b minus a over n part. And then we have the function at the end plus twice the function at the first interior point, twice the next point, twice the next point, so forth and so on. And then at the end, just once. So if you look at the coefficients, 1, 2, 2, 2, 2, up to 1. In essence, what this is saying is we like the points in the middle more than the points at the very end. Points in the very end are sort of less informative. They're giving us a little bit less information because maybe something crazy goes on at the end. Now, why the 2 here in the 2n? Well, what's happening here is you're taking your data and you're weighting it. And most of the time you weight it an average of 2. And so you have to compensate for your higher weighting. So that's why that 2 is there. All right. So we have our linear approximation. And the key is linear, that says you have 2 degrees of freedom. So you have to get 2 pieces of information. So we use the 2 endpoints. Now we go to Simpson's rule. And in Simpson's rule, we have this extra condition that says we are going to break things up, but we have to break things up into an even number of intervals. And the reason we're going to do that is we're now going to take two consecutive intervals, so not just one interval, but two of them in a row. And so we have this data, and who knows what our function is doing. It might be doing something interesting and exotic, but we're going to say, you know what? We're going to approximate it as though if it were a parabola, or if you like, a quadratic. So it's a quadratic approximation. Now, in order to get a quadratic, I need three pieces of information. So that's why I'm gluing two intervals together, because when I glue the two intervals together, I really have the three pieces of information. Namely, what happens at the left, what happens at the point where I glue, what happens at the right. So, how does Simpson's rule work? Well, again, n must be even. The b minus a over n, again, that's our width. So we're taking our interval from a to b, chopping up in n parts, b minus a over n, that's how wide each interval is. And now, the weighting's a little bit interesting, because it doesn't go, it kind of goes up and down. So it's 1, 4, 2, 4, 2, 4, 1. Now, if you think about what's happening, it says something kind of interesting here. Because where do we get a lot of weight? Well, the answer is we get a lot of weight at these points, which are the odd points. So it's like we feel like the odd data points are giving us more information, whereas the even data points, we're getting numbers like 2s, and at the end it's like 1s. So if you were to visualize this, suppose you took our interval and you had your data. So here's my x0 at the end, my little pinky, this one here. And what we're saying is that the points in the middle here are more useful than the even points. So it's like, oh, these points in the middle are giving us more information. Now, in essence, what that is reflecting is it says, you know, midpoints are really useful, and they should be weighted more. All right, so those are our formulas. Now, among these formulas, we do expect you to remember the trapezoid and Simpson's rule. And the trapezoid is not so bad. Simpson's rule, you got to remember 1, then 4, 2, 4, 2, so forth and so on. And what's really happening is you really have a 1, 4, 1 kind of weighting for each pair. And then what's happening is when you glue consecutive pairs together, this one will double up. That's why it becomes a 2. Because it's really a 1, 4, 1 there, then another 1, 4, 1 there, and so forth and so on. The 3, well, where is that coming from? Well, it sort of says, what's on average, how are you scaling your data? If you alternate between 4 and 2, on average you're scaling it by 3, so you got to scale back. Now you might say, can we go further? The answer? Yeah, you could. Now, you don't have to. And at some point you sort of say, we're not really gaining much by going further. But suppose we wanted to go further, what would be our idea? Cubic would be our idea, right? Because we go from constant to linear to quadratic. So the next one would be naturally cubic. What is that? Well, it says we're going to take now not 2 intervals, but 3 intervals together, and we have our function doing something. I don't know, that's a little bit extreme, but okay. And what we do is we say, all right, we have data points. Namely, we have 4 data points. What's the function at these points? And we can find the cubic function that best approximates those 4 pieces of data. Generally speaking, the higher degree of the polynomial, the more likely you're able to fit a curve. You're trying to do a better approximation. So this is actually, it has a name. You don't need to know this, but you know, sometimes it's fun just to know things. Knowing stuff is good. This is called Simpson's 3/8 rule. And you're like, ooh, 3/8, that's a terrible name. Well, hold on, we'll explain the name. All right, so here n has to be a multiple of 3. Why? Because we're breaking things up into 3 intervals to get our estimate. Now, how does it work? Well, the way it ends up working is it's similar to the quadratic, which is, I should weight these points appropriately. So here, quadratic goes 1, 4, 1. For a cubic, it turns out to be 1, 3, 3, 1. That's the right scaling. So in other words, the point on the left and the point on the right get scaled by 1, and the points in the middle get scaled by 3. So if you run it through, you get the following. You get your b minus a over n, and then there's going to be something that goes here. We'll talk about what goes here in a second. And then you get your 1, 3, 3, 1 pattern. So it will be f of x0 plus 3f of x1 plus 3f of x2 plus, now what comes next? The 2. Yes. So that's what happens. And then it's back to 3 again. And so forth and so on up until the very end. And so what's happening is you end up getting a 1, 3, 3, 2, 3, 3, 2, 3, 3, 2, da, 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 to the end, 3, 3, 1. All right. Now, what goes there? The answer is 3/8. That's why it's called the 3/8 rule. Now, why 3/8? Well, here's a simple way to think about it. If you think about what we're doing, we're sort of gluing 3 intervals together. So that's 3 intervals. But now, how much data are we sort of using? Well, we use this point on the far left once, this point on the far right twice, and then these other 2 points we use 3 times each. So we're using sort of essentially 8 times the data. And we're saying, well, for 8 pieces, really should be counting for 3. So I need to scale by 3/8 to do that proper adjustment. Now, why don't we go and talk more about Simpson's 3/8 rule? Well, it is more complicated. And in terms of how does the 3/8 rule compare to just Simpson's rule, it's not a huge improvement. And so it's like, okay, that seems reasonable. All right, let's do an example. This came from the exam from last spring. Whoa, should be a good problem. So during a heavy snowstorm early in the season, and last year there was a lot of snowstorms. So this year, not so much. You're measuring the rate of snowfall at regular 1-hour intervals from the start of the storm. While preparing a summary of all snowfall over the entire season, you find that you have lost some data for this particular storm at the 2 and 5 hour mark. See, there's these holes right here. So we have some of our data. So we have this storm. We know we kept track of what's happening at certain times. So 0, that's the storm began, 1 hour after it began, 2 hours, and so forth, and so on. And then we have what's the rate of the snowfall? How many inches per hour? Because we could measure that. We went outside, measured it, went back inside. All right. Now, what do? Well, searching through our notes, we see that before we lost the data, we'd gotten an estimate for the amount of inches which fell during the storm. And what happened is the way we got the estimate, we used all the data, and when we did the trapezoid rule, our estimate was 20 inches of snow. And when we did Simpson's rule, the answer was 22 inches of snow. And use this information to fill in the table. So essentially what we have is we have 2 facts. We say we know what happens when we estimate by the trapezoid rule, and we know what happened when we estimate by Simpson's rule. So that's 2 pieces of information, and we need to figure out 2 things. So that's good news. Now, one of the things you might say is, shouldn't our estimates be the same? Why are we getting different numbers, 20 and 22? Well, that's the thing about estimates. They're estimates. They're not precise. So you can get different estimates depending upon which type of measurement you're using. And of course, people can use this to their advantage by manipulating the data, saying, look, I'm going to take my data and measure it in a way which is beneficial to me. Well, okay, so you always should be suspicious whenever anybody volunteers to report on their own data. All right, so here we go. What do? Well, we're going to use all the data. So we think about trapezoid rule. So trapezoid rule says, well, let's give these names. I'm going to call this missing entry A, this missing entry B. Because these are things I don't know, but I want to give them names so I can work with them. So the trapezoid rule says I need to know my width. So the width would be the length between consecutive times. So what's our width here? 1. Okay, so that's good. So our widths are 1. So our trapezoid rule says it's your width divided by 2 times, you take just your first entry, which is 2. Then the second entry, you double it. So 2 times 1. Then you double your next entry, that's 2 times A. Then you double that next entry, and you're really doubling everything in the middle until you reach the end, and that one you leave alone. All right, so that's what we got from the trapezoid rule. So I'm just taking the values at the end, that's the 2 and the 4. Everything else gets doubled, and I add it all up. Now, according to that, the trapezoid rule, we should get 20 inches. So that's equal to 20. So, through the miracle of math, we can simplify this. So, for instance, I can multiply the 1/2 through. This becomes 1 plus A plus 5 plus 3 plus B plus 2 equals 20. Or there's an A plus B. And let's see, what else do we have? 1 and 1 and 5 is 7. And 3 is 10. And 2 is 12. So that's 12. I'll move that to the other side. And I get A plus B should be 8. So there's some information. So we can recover from what we know about our estimate for the trapezoid rule that A plus B should be 8. Okay, well, now we'll do the similar thing, but Simpsons. So Simpsons, okay, we have the width is still 1, and then we divide by 3. And now we have to remember, how do we scale? So, how do we scale this number? 1, right? So we times it by 1, we get 2. How much do we scale the next entry by? 4. Good. How about here? 2. Here? 4. Next one? 2. Next one? 4. Last one? Yeah, let's go by 1, so we get 4 out. Good. Equals 22. All right. Well, up here, the 1/3 goes through pretty well. Maybe not so well here. So instead of multiplying the 1/3 through, because that would give me more fractions. My goal is less fractions. So how can I get rid of this 1/3? Yeah, take it to the other side. So fractions are, I don't want to say our enemy, but they're trying to trip us up. So we want to be wary about them. We're going to keep our eye on them. So we have the inside, 2 plus 4 plus 2A plus 20, which is 4 times 5, 6, 4B and 4, and that's going to equal 66. All right. Now, well, we have the 2A from there, the 4B, and then what do we have? We have 2 plus 4 plus 20, it's 26, plus 4 more makes 30, plus 6 makes 36. So I'll do an intermediate step. Plus 36 equals 66. Well, of course, we can take that over. 2A plus 4B equals 30. Well, now we can divide by 2. A plus 2B is 15. So that's good. So now we have our other piece of data. So all we did, I don't want to sound like it's trivial, but we just said, what's the rules? Apply the rules and see where we get to. And what we got to is we got to 2 equations. So we know that A plus B has to equal 8, and then A plus 2B has to equal 15. Now what do we do? Well, we solve. 2 equations, 2 unknowns. Lots of ways to do this. Here's a way. I can cancel off the A's. If I subtract the top one from the bottom one, what happens? The A's cancel. I have negative B plus 2B, which is B. Negative 8 plus 15 is 7. So now I know B. What is A? 1. Because A plus B has to equal 8. And there's our data. So we filled it in. All right, so there's an example. That was a fun problem. I like that problem. Okay, so a few more notes to make here. So we have our trapezoid rule. Most of this repeats what we already said today. So don't panic too much if you see this. It's the same thing we've talked about already. There's the pattern 1, 2, 2, 2, 2, 2, 2, and then 1 on the end. But there's something I want to bring up, which is the error. We've talked about approximations, but the thing to keep in mind that approximations are only useful if you know that the error is small. So if you say, it's 10 about, well, okay, 10 within how much? If you say, well, it's 10 within about a half, it's like, okay. But if you say it's 10 plus or minus 20, not very good. It's something like, we're in the political season right now. You see these polls. Well, this candidate is polling at 1%, plus or minus 3%. So maybe they're at negative 2%, who knows? But, there's a lot of error in these things. The smaller the error, the more confident we are in our answer. So what we want to do is try to say, okay, how confident are we in this answer? That's what we want. And for computers, this is important because we want to say, all right, you gave me a number out. Can you be sure I'm close to this number? So we want to have ways to check. Now, we're going to talk about the trapezoid rule. We'll also talk about Simpson's rule. There is formulas for them, and I want to be clear and state it explicitly right now so you hear it. We will not expect you to memorize these formulas. We will expect you to be able to use these formulas, which is our way of saying, if we ask you about the error, we will hand you the formula. The question is, can you work with it? So here we go. We want to say what's happening with the trapezoid rule. So what could cause our error to be wrong? Well, our error would be wrong if our function wasn't flat. So we want to have something that's measuring how unflat it is. So flat would be, first derivative is great, we don't care. The second derivative somehow measures how unflat you are. So we look at our second derivative, and we have the following. If our second derivative is not too large, so m is some bound on how large the second derivative can be. So we're bounding our second derivative, which means that we're trying to really say, how unflat can you be? So that's the idea. The smaller that m is, the more flat it should be. Okay, so we look at our second derivative. We bound it by some value m between a and b. So then the error of our estimate, if we have our n steps, is bounded by that size, this size of how big f double prime can be, times b minus a quantity cubed, and then divided by 12n squared. Now, one of the things that you should note is this says the following. If we fix a, so if a is fixed and b is fixed, m is also fixed because m depends on what's happening in the interval. So in particular, this says that if you want to have a good approximation, the larger you make n, the smaller it will be. And in particular, as long as you let m be sufficiently large, it will be within any reasonable bound. Of course, sufficiently large might mean millions depending upon the situation. All right, so how do we use this? So suppose we have a function, and we know that the second derivative is at most 6, between 0 and 2. Then how many steps should we choose if we want our error to be at most 0.0001? Now, let's be a little bit careful here. When we say we bound our error, it doesn't mean we solve for our error. We just say we want it to be contained. So we're not claiming that after we get our answer that says, if you want an error of exactly that amount, this is how you pick n. What we're saying is, look, if you pick this value of n, it's definitely smaller than that amount. All right. So now, essentially what you do is you just work to identify your pieces. So you say, all right, this part right here is our error. So that goes into the error part, the size of the error. So we have 0.001 is less than or equal to. Now we need to figure out what is m. Well, what's m? 6. Yeah, so this is our m. So 6. What's B and A? Yeah, we go between 0 and 2. So it'll be 2 minus 0 cubed. Divide that by 12 n squared. So 12 is a fixed number, and we don't know. That's what we're looking for. Well, these aren't so bad to work with. Now, 0.0001 is another way of writing 1 over 10,000. Because there should be 4 zeros. Every 0 you add is a moving the decimal point over. And you should move it over 1, 2, 3, 4 times. So that's why it's 10,000. And I'm just using that because I don't have a calculator. So for me, it's easier to work with whole numbers. All right. Let's clean it up. Upstairs, we have 48. Downstairs, we have 12. So 48 over 12 gives us 4. So we have 10,000, 1 over 10,000 is less than or equal to 4 over n squared. All right, what do we need to do to solve for n squared? All right, we can multiply through. Aha. Sorry, I'm just checking here, just making sure. Ah! That's why I got this wrong. Okay, all right. Sorry. Ha 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 ha. Oh, ha, ha. Less than or equal to 0.0001, which is equal to 1 over 10,000. Okay, good. There we go. Now we're back on track. Because remember, we moved it over 4 decimal places. Now you're probably thinking like, what just happened here? Okay, so I was wrong to point to this to be the error. This is not the error. This is what we want to bound the error by. So we want our error to be below this. We say, well, what do we know our error is below? We know our error is below this piece right there. So our error is below that piece. So what we say is like, okay, I want to make this piece below 0.001. So that's why the inequality should have been there. Okay, all right. I apologize for the confusion. Completely my fault. All right, so cross multiply, and you'll get 40,000 equals n squared. Oh, sorry, less than or equal to n squared. We can preserve the inequality. You always have to be a little bit careful when you're working with inequalities. If you multiply by a negative, make sure you have to switch the sign. If you flipped both sides, you'd also have to flip the sign. When you cross multiply, well, the numbers we cross multiplied by are 10,000 and n squared, and they're both positive numbers, so we're okay. All right, so we know that 40,000 is less than or equal to n squared, so what do we need to be true for n? Yeah, take the square root of 40,000, and it's not just a random number. We picked a number we could actually take a square root. So that says 2,000 has to be less than or equal to n. So that says, sorry, not 2,000, 200. If you pick 200 intervals, then our error will be off by at most that much. Now, 200, for a computer, that's great. Loves 200. If you're on an island with coconut technology, not a good choice. Not a good choice. But, oh well. We'll try to avoid doing too many coconut problems on the exam. Now, for Simpson's rule, what happens? Well, the error is similar. So again, this is sort of a summary of Simpson's rule. We've already talked about all the big ideas. For the error analysis, it's similar except for a couple things change. What changes? Let's pull up our trapezoid rule to compare side by side. So the trapezoid rule says you should be looking at the second derivative because you want to look at a line. That's what trapezoid rule does. Now, Simpson's rule says, look at the fourth derivative. Now, you're probably thinking, whoa, we went one derivative too far. Because we're looking at quadratics, right? Somehow, that should only be one more derivative up. It turns out, this is kind of miraculous. Simpson's rule does a fantastic job on cubics. Fantastic job. So good that it's basically spot on. So you get one free derivative. So you look at the fourth derivative. All right. Now we say, okay, suppose the fourth derivative is bounded. So what's happening here is the fourth derivative is going to tell us how far off we are from applying Simpson's rule. How far our error is going to be off. The smaller the fourth derivative is, the closer Simpson's rule will be to matching the behavior of the curve. Then the error for the estimate, using Simpson's rule with n, and remember n must be even, equal steps, is at most, the error is m, and now instead of b minus a to the fifth, instead of b minus a cubed, it's b minus a to the fifth, and downstairs it's a different number, but here's the key. This is why we like Simpson's rule, because it doesn't sound like it's a huge difference, but look at that n to the fourth. N to the fourth is better than n squared. That says we're going to get much, much faster convergence. Because the higher the power of n, that's going to make your denominator smaller sooner. And therefore you get things to converge faster. So that's why we think of Simpson's rule as being a better rule. Our error tends to do better. All right, so we'll do the same thing, and this time we won't mess up. So, I hope. All right, so we have our fourth derivative is bounded by 90 between 0 and 2. So the fourth derivative, this is our m. Here is our a and our b. So we're going to have 90, and 2 minus 0 to the fifth. Divide that by 180, and then we have n to the fourth, which we don't know. Now, this bounds our error, and we want our error to be at most 0.0001, so we want this to be at most 0.0001. By the same idea. If we can bound this by 0.001, then our error is also bounded by 0.0001. All right, well, we do a little bit of work. Well, let's think about upstairs. You have 90 times 2 to the fifth, which is 32. That sounds a little bit complicated, but we can save ourselves some work. Notice that 90 and 180 are very close to each other. How close are they? Yeah, it's off by a factor of 2. It's like, oh, there's a 2. There's 2 to the fifth. I can cancel a single 2 upstairs with the 2 downstairs. So that's 2 to the fourth. So now what do we have? Well, we have 16 over n to the fourth has to be less than or equal to, and again we'll write it as 1 over 10,000. Cross multiply. 160,000. Ooh, that's a big number. Has to be less than or equal to n to the fourth. Now what? Take the fourth root. Exactly. Now you're probably thinking, oh, that looks terrible. But where did 16 come from? 16 is 2 to the fourth. And how about 10,000? Well, that's like 10 to the fourth. That's 4 copies of 10. So when you take the fourth root of 2 to the fourth times 10 to the fourth, what do you end up with?
20.
You end up with 20. So n has to be at least as large as 20. Now, that's the power of Simpson's rule, because that fourth root is going to knock these terms down faster. So you usually have to have much fewer number of data points to get a better estimate. That's why we like Simpson's rule. Okay, so there we go. Well, now that we're done with numerical integration, I guess, are there any questions about our numerical integration, what we've talked about? Okay. Well, let's have a nice, relaxing, just a simple, ordinary integral. Nothing fancy, no surprises. We need like a cool down. Okay. All right, so here we go. That looks pretty straightforward. So integral -1 to 1, 1 over x squared, that's like x to -2 dx. What's the antiderivative of x to -2? Yeah, so you add 1 to the exponent, x to -1. You throw a negative in front, so it becomes -1 over x, evaluated from -1 to +1. All right. So, what is that? Well, plug in 1, you get -1 over 1, subtract -1 over -1. All right? Yes, have I done that right? Okay, let's see what that is. Oh, I missed a parenthesis. No wonder you were concerned. Okay, so these two negatives make a positive. -1 subtract 1 gives us -2. All right, that was good. A nice cool down. Now, are you suspicious of this answer? Yeah, you should be, because it's like, this is too easy, Steve. You're trying to do something to us. And if you're not suspicious, let me try to make you suspicious. 1 over x squared. It blows up at 0, right? But the other thing you should note, even if it didn't blow up, one thing that's true about 1 over x squared is that it is always positive, because you square it. There's no negative sign. So what we're saying here is that when we integrate, integration can be thought of as finding the area. So we integrate this, and lo and behold, this has area -2. To which we sort of say, huh? What? Does that seem right? No, it does not seem right. Okay. I don't think we should have a negative area when our function is always positive. So something's wrong. So, what's our problem? What's different than what we've been doing before? Well, we don't need absolute value. I'll give you a hint. It's over here. Actually, it's over there. It's infinity. Yeah. The problem is you have infinity is involved. And infinity is a tricky thing to deal with. It's caused mathematicians to go insane for hundreds of years. The good news is we'll avoid that part of infinity. And you're probably thinking, whoa, how many parts of infinity are there? Turns out there's infinitely many kinds of infinity. But that's a different discussion. All right, so we're going to call these improper integrals. So any time that there's an infinity involved, it's improper. Now, why having an infinity, why is that a problem? Well, the problem is the way we do integration is we break things up into small parts and estimate each part. Now, we could have infinity involved in a couple of different ways. So one way is we could have it as a vertical. So this is an example of a vertical type of infinity where we have an asymptote. Now, our problem is when we break things up into pieces, one of our pieces will involve that infinite height. And that small piece, no matter how narrow it is, it's hard to compensate when you're infinitely tall. So that's a problem. Now, the other kind of way we can involve infinity is horizontal, which means that there's an infinity in our limit. All right, so we have an infinity at one of our endpoints. Could be both endpoints. Now, what's our problem there? Well, our problem is that we're breaking our shape up into small strips. But the problem is I only have n strips. One of my strips is going to have infinitely long part. So it's like an infinitely long piece for the base. And no matter how high it is, it's hard to compensate for infinity. So when there's infinity involved, our idea of breaking things into small parts, understanding each part and adding it back together is going to break. Now, the worst case scenario, and this can happen, is that there's infinities both vertically and horizontally. So that's an interesting case. Okay, so I claim that these are examples of functions which involve, well, they're improper. They involve infinities horizontally and vertically. So let's just think about it. Which ones are which? 1 over x. Is that vertical, horizontal, or both? It's vertical. Why is it vertical? It's vertical because there's an asymptote for 1 over x. Where is the asymptote at? 0. And notice that 0 is our bound. Now, if I had asked the question, integral 1 to 2 of 1 over x dx, is this an improper integral? No. We're happy with this one, but this one, we're not happy with, because we have to deal with infinity. So we have to deal with it in a special way. How about this one? Integral from negative 1 to 1 of 1 over square root of 1 minus t squared. Proper, improper, or why is it improper? Well, we can spot horizontal right away. So the way you spot horizontal is you look in the bounds. So you'll see, anytime you see an infinity or a minus infinity showing up in your bounds, then for sure it's a horizontal problem. Vertical, what do you look for? You ask yourself the question, does it have an asymptote? If it does the asymptote lie within the interval in which you're integrating, including the endpoints? Then you have a problem. If it doesn't lie within the interval, so here we said 1 over 2 of 1 over x is perfectly fine. Because yes, 1 over x has an asymptote, but it's far away. 0 is a long ways away from being between 1 and 2. Does this have any asymptotes? 1 over the square root of 1 minus t squared. Where are they at? 1 and negative 1, which means that we actually have 2 problems on this one. How about 1 over the cubed root of y squared? It has a problem at 0. So sometimes your problems are going to be at the endpoints. Here, this is a problem at 0. So you have to be careful. It's not always going to be at your endpoints. E to the x, that's a pretty good function. No asymptotes there. How about 1 over x squared plus 1? Are we good? It's a great function. Any asymptotes? No. 1 over x cubed plus 1. How about that? Any asymptotes? Yeah. So this one has an asymptote at negative 1. So there's definitely a problem here. That was supposed to be an at sign. That's not a very good at sign. All right. So those are what improper integrals are. Okay, so you know what improper integrals are. How do you handle them? What's the key? So the way that you deal with an improper integral is essentially, you think of it as getting closer and closer from a proper integral. So first off, we say, is it improper? We just quickly check, are there any infinities involved? So we look for our bounds, and we look to see if infinity shows up as an asymptote. So a division by 0 usually. There can be things which don't necessarily say division by 0, but cause asymptotes. Tangent, for example, is a function which has asymptotes, but we don't usually think of it as like, oh, I'm dividing something by 0. Once we've identified our problems, if there are any, we're going to break our integral into parts. One for each infinity. So if you have multiple problems, you're going to have to break your integral into multiple parts. You have to handle each part separately. And this is important. After we've done that, what we're going to say is, okay, for each part, I'm going to figure out what's the value by moving away from where I'm at. So usually when we've broken things into parts, one of our bounds is where we have our infinity. Either it's the 0 to 1. It's like 0 is our asymptote. So we would say, well, let's not go from 0 to 1. Let's go from b to 1, where I think as b as a small number, close to 0, but not 0. So I'm sort of like, let me pull back just a little bit from where that asymptote is and do that integral. So when we pull away from that asymptote, we no longer have an improper integral because we now have something which doesn't involve infinity, which means we can find the answer. All right, so we carry out an integral where we have some undetermined endpoint. Now we say, okay, let's move b closer and closer. So maybe my b was saying, I had a problem at 0. I'm going to now move it closer and closer to 0. And what do we do? If that value approaches a number, we say, okay, that's the value of the integral. If it blows up, we say integral doesn't converge. If you break things into parts, every part has to work. If even one part fails, the integral does not converge. But if all the parts work, you put them together. Now we're going to do a lot of examples in the next couple of lectures. So we're going to get pretty good at this. One thing you should remember is our good friend L'Hopital. Oh, L'Hopital. Remember, we have limits involved. And oftentimes limits involve 0 over 0 or infinity infinity. And so L'Hopital says what? If you have a fraction and it's going towards 0 over 0 or infinity over infinity, you can look at the derivatives, f prime over g prime, and ask what does that go to. And if it converges, then that's also what f over g converges to. All right. Now, you'll notice here that we said something on number 2. We said, break the integral into parts and handle each part separately. And you're probably thinking, do I have to do that? Would it really matter if I just did it all at once? So let's look at an example, something harmless. In fact, let's look at an example next time, because I think our class time is about up. And this is too good to go fast. So we'll pick up here next time. All right. Have a good day.